The nice thing about using targeted and nutritive therapies is that the cancers can no longer attract the shell anymore. And what happens over time is that their capacity to build this shell around themselves becomes less and less possible. And that's because they don't secrete the factors that draw out the cells that form the shell. So what you do then is come back with some kind of immune therapy as either maintenance or as down the road therapy. So there is a path forward, but it has to be rational, logical, and sequenced.
Welcome to Target Cancer Podcast. My name is Dr. Juneja. I'm a hematologist and medical oncologist, also known as the Onc Doc on social media, where we try to educate and do a bunch of stuff. Today is super special because I have basically one of the biggest reasons I actually went into oncology. And believe it or not, Sid, you may not know this, is also like I get a little style when I see your picture sometime. I'm like, ooh, I kind of like that. I think you have a shirt just like this. So we have the Pulitzer Prize winner, best-selling author, the person that really bridges kind of academics of oncology with philosophical, just ideas of how everything is interplayed, Dr. Siddhartha Mukherjee, who is here to talk about hopefully a couple of things. But the thing that I find really interesting, which is one of the questions I get most on all my social media stuff, is diet, diet, diet. What can I do for diet, to prevent cancer? But especially, I get a lot of questions when people have cancer. And it's super frustrating because a lot of times the medical oncologist answer is, well, you want to do this and that, but nothing concrete. So, Dr. Mukherjee, thank you so much for being here, and we're excited to have you.
My pleasure. Thank you for having me.
One of the things, and I think anyone that kind of follows my educational handle stuff knows about your book, Emperor of All Maladies. It's always the one that I kind of, recommend when people are kind of faced with a cancer diagnosis. One of the biggest things about cancer, as you know, and it's kind of the reason for the book I'm trying to write, which is it's time to cancel the term a cure for cancer, because it's very deceptive, right? You're basically trying to take something that arguably was almost celestially orchestrated or divinely orchestrated to have so many fail stops. That is the human body through evolution, cells. What if this doesn't work? What if that doesn't work? You try to take all that, like over hundreds and thousands of years, the mechanics and algorithms, and you're trying to basically now have to fight it when those same mechanisms are in place, but all of a sudden it's going rogue. And it makes it interesting, but also, again, deceptive, because it's hard to find a cure. There's all kinds of mechanisms in place. One of the things outside of targeted therapy that we talk about in precision medicine and saying, okay, this is the on switch that makes it grow, and this is the thing that's making it escape immunity, so stop that. You're frantically trying to, keep everything up to speed with as quickly as the cancer, which I kind of relate to viruses, grows. But you're looking at also what are the tools it uses outside of like necessarily the targets that we use and the immunity. And you're looking at basically amino acids or the fuel or the gas, potentially, if that's not too kind of rudimentary, on are there some cancer types? And pancreatic is one of them, which you always say, why is it so stubborn? It makes, it recruits your own cells. It uses fibroblasts to repel other people, microenvironment stuff. But you're like, let's look in to see, like, really, are there some tools that it's using that does make it unique? And is that where you started with talking about these amino acids in pancreatic cancer?
Yes, but maybe we should take a step back.
Yeah.
The step back, it goes back to the 2000s and the early 2000s. Now, cancer is, of course, a genetic disease, even if it's caused occasionally by viruses, like human papillomavirus or Epstein-Barr virus. But it's essentially these viruses or genes themselves are mutated, and ultimately cancer is a genetic disease. Genes are mutated. Those genes turn the normal processes of growth abnormal. Those cells now grow abnormally. I liken it to saying it's like a car where the accelerators are jammed, the accelerators being the accelerators of growth, or the brakes are snapped so that the cell can no longer have its normal ways of dividing.
Right. And the key is when you say genetic, and that was one of our podcasts, is we don't mean necessarily that was an inherited genetics, right? So people, I think, often mistake that to mean like, oh, but I don't have it in my family. We mean things that 85% of the time, it used to be 95%, now we're saying, okay, maybe we've learned about some more. But 85% of the time, it's something that was errors in these genes with replication of billions of times in your lifetime in your lifetime that causes these errors.
That's correct. So there are two kinds of, or there are three kinds of errors that can be caused, right? One is, we talked already about viruses. Viruses can come in, tamper with your genes, make your cell behave abnormally. The second kind of error is that you unfortunately inherit something from your family which gives you a higher risk of getting cancer. That would be genes like BRCA1, P53, and other syndromes, and those patients have higher risks of cancer. It's a little bit hard to quantify that number because that number keeps changing. We used to think that they were single genes. They're single genes that are very strong in their effect, but now we know that there are other patients who have multiple genes, 10s, 12s, 15s, maybe even hundreds, that they inherit from their parents, which raise their risk of cancer by 5-fold, 10-fold, 7-fold, 8-fold, 10-fold. And then there are finally genes, which are probably the most important set of genes that are mutated, that change because when cells divide, they make copying errors, like a photocopier makes an error in making photocopies. When a cell divides, it's a photocopier. It makes a change, and that change happens to be in a gene that controls cell growth, and that contributes to cancer. So very broadly speaking, those are the categories. Now, going back to the 2000s, we, and as a community, I say we, had this idea that since cancer is a genetic disease, then it must be the case that if we could find ways to block the products made by these genes, proteins, we would be very successful. And many drugs came out of that. Drugs like Gleevec, drugs like Tarceva came out of the genetic sequencing and the genetic understanding of cancer. And they were very successful. Some of them, like Gleevec, are extraordinarily successful. And then in the 2010s, we began to feel that we're a little bit stuck. That was a very humbling moment for everyone because we thought that we had solved the basic pathway, not the answer, but the basic pathway by which we would move forward in cancer research. But we began to get stuck. And the stuckness had to do with the idea that these genes, many of these cancer genes, cancer-causing genes, just weren't great targets for drugs. I'll give you an example. I treat leukemia, and when I treat leukemia, I know exactly which genes are mutated. I can tell you their names. They're not relevant. TET2, DNMT3A, who knows? You can call them various names. And when we tried to see if they could be targeted by either drugs or any other molecules, we never found really good ways to target them. That was problem number one. Problem number two is that even, and this is really, really, really important, even when we did find ways to target them, especially really the ones that were strong drivers of cancer, what happened is that the cancer cells, because they're evolving all the time, found ways to go around that target. It's a little bit like, we would find the Achilles heel of cancer, and we'd be very happy and congratulate ourselves, and we would drive an arrow into the Achilles heel of cancer, and the cancer, growing so fast and evolving, would just take the arrow out and throw it away.
Yes, and to that exact point, that's where the way that I think people understand is the same way was like with COVID. I thought we vaccinated against. I thought it's over. The same way that viruses kind of like grow and then they get these variants, right? They look different. Well, why do I need another booster that's more comprehensive? What does that mean? Well, if that protein that you're attacking, that M spike or that M protein on the initial, they just get smarter. It's like the selection pressure of viral illness. But in this case, with therapy, they all of a sudden, in their desperation, they're like, okay, I can undergo calamity and basically try to find any escape to where this thing isn't needed anymore. The same way when we block hormone and...
To clarify one thing with both viruses and cancer, it's often a misconception that the cancer is evolving as we give the therapy. That's not the case. The cancers and the viruses, because they're mutating all the time, and they have millions, billions of mutations, what's happening really is that there's already, and I have to emphasize this, there's already
The
a
variant.
version, a variant that is resistant.
Correct.
And all you're doing is killing off everything else and selecting that variant.
Exactly.
This was a big realization, actually. Cancer doesn't have a brain, and viruses don't have brains either. But they do have mechanisms by which they mutate. And if you have a billion of them, then there's a chance that one of them has already, even before you start the therapy, has already developed a mutation that will cause it to resist your therapy.
So then the term, I'm happy you said that, because the term, we had Dr. Keith Flaherty talking about, in some sense, like the immune system play and everything like that. But we use this term escape mechanisms. But to your point, and it's a very good one, is when people say, well, chemo, they actually are not curing the cancer on purpose, right? That's one of the things I get on social media. And it's like, it's hard to explain why after 9 months, 14, 18 months, especially like you said, EGFR, Tagrisso, and all these things, it's hard to explain to somebody, short of testicular, where you can cure it with chemo, how you can't see anything, but it still always comes back. And there's this, you learn from kind of opinion, because I think it's better to just accept where it's coming from than fight it. And the thought is, well, then why is it coming back? How come if it all went away, it comes back? And to your point, and even that term escape mechanism, which they always talk about in colorectal with now they're not using this pathway. What you're saying is it wasn't an escape. It turned out to be an escape, like in retrospect, because it already underwent something that was not going to be this basically vulnerable to what the initial chemo and the initial tumor burden was.
That's what all the science shows thus far.
That makes so much more sense.
That the mechanism by which a cancer stops responding to your therapy, even if it's targeted therapy, is not because it has a brain and
Right.
figured out that, this is the way I'm going to escape it. It is because it already possessed a mutation that would have allowed it, in any case, to escape the toxicity of the drug. This has many, many, many consequences. We can come to that in a second. It has many consequences for how we think about therapy, how we build therapy, but we can come to all of that in a second. All right. Now, in the 2000s, we thought that if we found enough drugs that would kill the cancer cells, targeted drugs especially, we would conquer cancer. And some of them were very successful. We talked about Gleevec being really the best example for a cancer called chronic myelogenous leukemia, or CML. Gleevec really takes that cancer and puts it into one of the most profound remissions that has ever existed. We were so excited. And we thought that all cancers behave like this, and we'll find these Achilles heels for all cancers, pancreatic, colon, etc. And that's how things are going to go ahead. And then reality hit. It hit slowly, and now it's hit really hard. And by hard, I mean that we've found in two problems. Problem number one is that cancers, some genetic mutations that are in cancers, we don't even have drugs for, and we can't even seem to find them. Problem number two is that when we do find them, they have they undergo resistance. The most striking of these is, after decades of work, we found a drug, a group led by Kevin Shokat and others, found a drug that was exquisitely specific to block a pathway that is considered one of the central mechanisms of many, many cancers. And when they used the drug, the extension of life was like 11 months or 10 months. The cancers grew resistant and all the patients died. Similarly, work done by Luke Cantley, who's of course my collaborator, we'll talk about all of that, found drugs against another very prominent gene that's mutated in cancer called P10. Same story. When it was applied, the extension of life was a few months.
But to your previous point, do we call it resistance then? Or is it that it just satisfied the initial, tumor biology and molecular sequencing of what we biopsied, and really just we're already behind the new one that was going to be P10 resistant, or previous one you mentioned? It's, you know what I mean? Like the semantics then, because you really injected this interesting thought to me about how, is it escapes, is it resistance, or is it just sheer serendipity of sorts, like fortunate for the cancer, where it's already ahead of you. Like you've already had this variant that exists.
So let me say a few things about that. Bert Rogoldstein, who's probably one of the smartest cancer researchers on the planet, always says that there are 3 zeros between 1 billion and 1 million. If you have 1 billion cancer cells in your body, that's 1 billion opportunities that the cancer cell has to have a mechanism by which it can resist a drug. If you have 1 million cancer cells in your body, it's 3 log, or 3 times 0, 1,000 times, less likely to create resistance against the drug.
Right.
So keep that in the back of your mind, because numbers matter. But let's go back to the story that I'm trying to tell. We then began to realize that maybe it's not the cancer cell that we should be attacking only. We can still attack the cancer cell. But really what the cancer cell has built around itself, the home, the nest. And that nest has many components. Cancer cells need nutrients, they need blood vessels, they need to build a tissue environment around themselves, almost like an organ. And maybe we should be, instead of killing cancer cells only, we should be focusing our attention on these metabolic pathways, the nutrient pathways, the nests that the cancers build around themselves, the blood vessels that they draw, the immune system that can or cannot look at them, etc., etc., etc. So by the mid-2000s, a new idea is and was being born around cancer. And that is that let's not attack just the cancer cell. Let's attack these homes, these nutrients, these metabolic pathways that cancers build around themselves. And that's where I come in. That's where I grew up. Because I, like many other people, was disappointed but also excited about the idea that maybe the problem is not just the cancer cell, but this home, this environment, microenvironment, nutrient environment, metabolic environment, immune environment, vascular, blood vessel environment that the cancer builds around itself. The advantage of these environments is that unlike the cancer, they don't mutate. There aren't billions of them. They are relatively static. And that's where I began to think that, oh gosh, maybe my work should be not around sequencing cancer cells and finding drugs that kill the cancer cell, but rather thinking about what the cancer cell builds around itself, metabolically, vascularly, blood vessel-wise, its home, etc., etc.
I'm so sorry to interrupt you, but the one thing that I think about, again, with these kind of allegories to just like human life as a whole, is the same strategy they used in medieval times, right? If you had a castle and you had a whole bunch of people in there and you knew you couldn't really overtake the castle, it was a strategy to basically say, well, heck, we're just not going to let you bring food and water and just starve the people inside. Yeah. And they do it even in modern war. Yeah. Right.
We would burn the fields around the castle and starve the people.
Right. Without having to attack those gladiators, they starve. Like and they do it for war even advanced. Like, oh, let's not let them get their weapons across this way. So it's like, they're powerful, but you just want to dismantle the things.
That would be, and that's a strategy that I thought would be very interesting.
That's wild.
And so when I launched my cancer career, it was all around that strategy. It was all around, I don't sequence cancers. I mean, I sequence cancers medically, but that's not what I do as my sort of intellectual living. What I do is I think about cancers and I think about what homes they build. If you think about, again, your analogy, like who's bringing in the food into the castle? What food is it? And can I block the food? Can I block the blood vessels? And that's how Faeth started. Faeth started with this idea that it's great that you can find drugs against the cancer, but let's also block the mechanisms by which the cancers are metabolizing, eating, growing, etc., etc., etc. And that's really the basis for Faeth as a kind of the intellectual basis for the company.
And that's interesting because you're leveraging what we know. People sometimes think of cancer as like this enigmatic, nebulous foreign thing, but it's not. It was once a normal cell of sorts, the one that started it all, and it has a bunch of the tools that we know about normal cells. So you're like, let's extrapolate that, like just knowing what the biology of cells are like, and seeing if we can. It's almost a back door, because now you're not trying to do the things that make it. It's like any of those shows and movies, the thing that makes it so scary, like this thing will never be defeated, like Venom or whoever. And instead, it's a backdoor. You're not trying to fight the things that make them so malignant, but instead say, dude, I'm not going to even let you have the tools to be able to like carry out your, that malignant effect, which is just so novel. And then the question, though, would be that I think a lot of people would, higher level, that think, okay, but then wouldn't that starvation cause a starvation, for your own intrinsic cells? And my guess would be no, because they're not as hungry. You're not on the sixth gear in that car.
That's a very important question. So there is a relatively narrow window in which we can find these metabolic Achilles heels. So it turns out that cancers, because they're growing so quickly and because they're dependent so acutely on nutrients, are different from normal cells. Now, this was known for a long time. German scientist named Otto Warburg knew about this in the 1900s, early 1900s, that cancers metabolize sugar differently than normal cells. Lots of scientists have known since that time that cancers metabolize amino acids, which make proteins, differently from normal cells. Lou Cantley and I showed that cancers metabolize sugar, especially when they're given stress with a drug, differently than normal cells. So there are, in fact, Achilles heels for cancers which will not affect normal cells, but will affect cancer cells, because the cancer cells are very, very acutely dependent on these amino acids for their growth. Now, you may have some side effects, but they're nowhere near what you would expect from chemo.
It's kind of like the same concept of cytotoxic chemo. Somebody might say, oh, well, if its cancer cells are normal and you're giving a poison from the yew tree, Taxol, whatever, like, wouldn't it poison your regular cells? Yes, but the reason that it's so effective, and the reason for the earliest phase 1 and phase 2, is give it enough for the stuff that replicates fast and gets the damage, and the ones that are slower, the hair ones, the GI ones, may suffer a little bit more. It's literally taking that concept but backwards. It's like saying, you need gas and change your oil at a certain frequency, but if you're in 6th gear in an M5, you're going to need it something different than being in 3rd gear at a lower speed and having a much less aggressive engine. It's the same-ish strategy of being able to distinguish the two in the cytotoxic realm, but instead in the provision realm, which is like what you're providing for it to be able to execute. So that's so interesting. And then, of course, I think it's the question would be doing both.
It's not just a hypothesis. It turns out that the genes that are mutated in cancer cells don't just mutate the growth of the cell or change the growth of the cell. They actually find mechanisms by which they can use these amino acids and use them in quicker ways, in faster ways. So it's like, once the brakes and the accelerators have been jammed and broken, in your car analogy, it's as if that the entire engine begins to say, I can use
corn oil, how they're trying to get fuel and gas with the corn products.
Whatever gas there is. I can use the gas in a fundamentally different way than I used to be able to use gas. And that's something that no one knew. But over time, we and others have found that this is what the genes do. They figure out different ways to use the gas and use the gas faster. And the faster that they use the gas, the more dependent, the more addicted they become to the pathway by which they're using the gas. In total, what happens is that they find a mechanism, and our job is to prevent them from finding that mechanism, and in fact prevent them from even using that mechanism to fuel their growth. Often people say, cancers eat sugar, so you don't eat sugar because you'll just fuel your cancer cells. That's not right. Cancers are more sophisticated than that. It's not like they're eating sugar. They're metabolizing sugar. And metabolizing and eating is a different thing.
Right.
Metabolizing means they're chemically converting things into other substances that allow them to fuel their growth. Eating means, obviously, ingesting something. So it's not like you aren't feeding the cancer in the sense that you understand, like in the common places. What you're doing is you're targeting very particular metabolic pathways, chemical pathways in the cancer, such that that addiction that the cancer cell has to whatever it might be, amino acids, certain kinds of sugar, etc., is disrupted. So when you go to your doctor, it's not like you're going to go to your doctor and say, I'm going to stop eating sugar. What you're going to have to do, if Faeth is successful, is you're going to have to find very specific, and we've found them already, very specific ways in which you interrupt or disrupt the metabolic pathways, the internal digestive system of cancer cells, such that they can no longer grow.
That's a huge statement. The internal metabolism. I hope people heard that. It's not your body, but the cell.
Yeah, it's not your body. It's the internal digestive system
of that cancer cell. Yes.
Yeah.
That's a huge point.
Yeah. So you cannot starve your cancer, as far as we know, although people have been trying this for a while. You can't starve the cancer by starving yourself.
You could, but you would die in the process. That's what I kind of say. I'm like, it's a technically correct statement. Yes, you can starve your cancer cells, but your own cells will die well before that. So like, it's that concept. There's no way that you can just completely block everything. It's not binary. One thing feed, one thing not. All of the ways that it processes everything are, you can't without literally killing the person in the process.
Exactly. So instead, what you do is you find the particular internal digestive system of a cancer cell, find the molecules that are part of the internal digestive system of the cancer cell that make it vulnerable to particular nutrients, and you block that internal digestive system without causing your whole body to starve. And there's a line or a window by which you can do that. After a certain point of time, if you kept doing that, your whole body would start starving. So somewhere in that window,
there's a sweet spot.
There's a sweet spot. And Faeth and we and all our scientists have found such sweet spots. There's not one, there are many. There are amino acids, there are kinds of sugars, etc., etc., etc. But it's not like, you can say to yourself, I'm not going to eat any protein and my cancer is going to go away. It's not going to happen. You have to find, as I said, the internal metabolism of the cancer, and we have target those and make sure that that doesn't affect the rest of the body, but slows down the growth of the cancer cell. Does that make sense?
That makes perfect sense. And I think the next question that, if anyone listened to previous podcasts, is I had one where I really wanted to delineate, the kind of almost rudimentary way we thought of histopathology as like, oh, this is how the cancer is going to behave. It's like, oh, it's adeno of the lung or, whatever. And these episodes help people appreciate how, dude, it's so much more than that. It's not just the histopath. It's like, okay, proteomics. Is it HER2 positive or not? And then, okay, now we're talking molecular. So the same way all of that stuff is complicated, and then, if you can use your BRCA pathway or not. We've dissected all these things. My next question, I think some of the viewers would say is, okay, Dr. Mukherjee, is this a carbon copyable observation, or is it something that you need to take your own, like, somatic tissue of that cancer cell, don't put it in formalin, take it and actually study that kind of like particular fingerprint and blueprint of that cancer cell? Or does everything look like it's actually, applies in some correlation to either a molecular profile or just even the histopath, I suppose, for that quote unquote pancreatic or whatever that tumor may be?
So it's an incredibly important question. How personalized does this have to get? And the answer is that so far, it seems as if these mechanisms are relatively general. I'll use the word relatively because it has a little bit of a dependence on what genes are mutated. Because some genes are particularly good at, as I said, hijacking the fuel. And those, of course, are the cancers that we want to send Achilles arrows to.
Right.
Some genes that are particularly good, but they're not like weirdly uncommon genes. These are common genes that are commonly mutated in cancers. So it's not like you have to do an incredibly complicated histopath
Right.
or an incredibly complicated genetic pathology on the cancer and then come back and say, oh, I'm going to only make a particular diet for you that's specific for you. It's much more that I would say that your cancer, like 15 others or 20 others or 100 others or 500 others, has a gene that has a particular capacity to use this fuel. We know this because of experimental data. So the diet that we're going to prescribe for you is X or Y.
Right. So you've
And
observed
so
that, and that's
we've
the
seen
answer.
that across
Right.
in real scientific models. Yes,
Right.
this is not a hypothesis.
Right. This is like, and that's the answer there. Is when somebody says, "Well, Sanjay, you always talk about like precision." That this is because that is, remember, the closest thing to a fingerprint without taking the cell is just doing the sequencing. If you observe that, hey, if it has XZ00, it seems to like use these amino acids XZ00. Ooh, let's test it. Oh, yep, sure enough, they all behave the same way. I mean, that's how you that is in a very basic way how we treat hormone positive breast cancer. If it has HER2, you use it. If you don't, you don't. Doesn't mean like eventually down the line maybe it's not working, this and that, but we know that works, and that's why a lot of people see it disappear up front. So that's super cool and interesting. Now, and I'm sure you were getting to this, so I'm just going to swipe it a little bit sooner, but we've said many times, and I've said, and Keith Flaherty says it, most experts agree, and I know you do because I already know the answer to this, so forgive me, but that the way we're going to like control cancer for a long time, if not cure all cancers, but at least control, it's going to be a multimodality thing, right? So you talk about immune therapy in your podcast with Peter and Tia and how phenomenal it was. You're re-enabling something that's always been doing what it's doing and got tricked for a moment, and you took off that, invisible cloak from Harry Potter, and all of a sudden it gets exploited and then it gets attacked. So you talk about immune therapy. We talk about the cytotoxics when that's appropriate for the replication. We talk about targeted therapies. Can this be done? Can I attack it from both ends? Can I attack that driver, that Thor hammer that the cancer is trying to use, and I hopefully can target it, or I have to use cytotoxic just because it's so fast, chemo? But can I also then like rob him of its calories and hydration and get him into an AKI basically by starving? Is it possible to attack it from both ends, or even triple end if we can incorporate immune therapy one day? Of course, it matters on the cancer type, but surely if this could be used concurrently with standard of care targeted therapies and cytotoxic, I mean, that just feels good.
There's absolutely no reason that this can't be used in combination.
That's amazing.
And in fact, there's absolutely no reason that we aren't using most of these therapies in combination. And that's why I said it's important to think about numbers. I love numbers. I'm sure you love numbers. There's a difference between 1 billion, 1 trillion, and 1 million. So what do? One rational way, and there may be many rational ways, but one rational way to do all of this would be when you have a big tumor, and when you have a big tumor burden, you use cytotoxics to kill most of your cells. So you do a 1 billion to 1 million reduction. Now, why does that help? It helps for many reasons, but the main reason it helps is it gives the cancer 1,000 less chances of becoming resistant.
Oh, see, I don't think to highlight that. That's so true. It's the rapid way of just trying to reduce the chance of these like variants that get smarter. That gives an interesting point to using immunotherapy alone for a high PD-1 versus like, and again, this is an extrapolation, versus triple agent, because yeah, you might say, oh, it's going to respond well, but we know immune therapy takes a while versus like if it's high burden lung, like, arguably, God, that's so interesting. Why wouldn't you want to knock it down cytoreductively and incorporate that immune therapy? That's such a huge point that has never been brought up on these shows. I'm so happy you said that.
So the first thing that you would do, rationally speaking, is cytoreductive therapy. And it's cytoreductive for several reasons. Of course, it relieves some symptoms, but more importantly, it reduces the number of chances that the cancer has to create a resistant mutation. And if it's a high disease burden, if you've got the cancer super early, you don't need cytoreductive therapy because you're already not at 1 billion cells, but at 1 million cells. All right, now you reduce the cancer burden, and now you use multiple angles of attack. One angle of attack is to use nutritive therapy so that you can starve the cancer. The second angle of attack is that while you're starving the cancer, you use targeted therapy. And the third angle is that we've now learned over and over again that immune therapies don't work for many cancers, and we started figuring out why. That's because cancers invent a kind of shell around themselves, a shell of other cells, a nest, a home, a citadel, a fort, whatever you want to call it. And immune cells can't get in there. The nice thing about using targeted and nutritive therapies is that the cancers can no longer attract the shell anymore. And what happens over time is that their capacity to build this shell around themselves becomes less and less possible, and that's because they don't secrete the factors that draw out the cells that form the shell. So what you do then is come back with some kind of immune therapy as either maintenance or as down the road therapy. So there is a path forward, but it has to be rational, logical, and sequenced. So you do cytoreduction to reduce mutational burden.
That's the immediate threat. That's the day-to-day threat of having this recurrence or resistance. Yeah.
And it's not going to go away. You use cytoreductive therapy, and then you slowly begin to choke and paralyze the cancer. And as you choke and paralyze the cancer, imagine going back to your analogy of the citadel, right? The citadel, if you burn the fields around the citadel, if you burn the fields around the fort, people in the fort can't come out anymore and start planting new fields. So what that enables it to happen is that the immune cells can start going in and potentially restarting an immune reaction. And we have other companies and other programs, I have and others have, other programs to do exactly that, is that once you've burnt the field, once you've burnt out the supply chain, as it were, for the cancer cell, you then come back with immune therapies of various sorts so that now they can enter the fort and start killing the cells themselves. So it has to be done sequentially and thoughtfully. And there are many blockades. We can talk in another program about what the blockades are. There's pharma companies that won't collaborate. There's some that will collaborate, blah, 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 blah. But there is a road forward. And the road forward is not just absurd. It's not nonsense. It's very logical.
Right.
Pieces that they're like, you build one on top of the other.
Right. It's not like you're just like, oh, I think one day, like, no, it's like we're finding the different ways to really, beat that thing, or not even that, I hate to use singular terms, but like you said, the sequence, and that's a point we haven't hit well, is very important. I'll do one more on top of that. I don't know how you feel about it, but I actually have a podcast coming up with a buddy of mine. He's a PhD. He went to Juilliard at first. And anyway, he said, Sanjay, the reason people aren't talking about this because it's not sexy. It's not targeted therapy. But what they're looking at is basically to putting like high intense, like triple levels of chemotherapy intratumorally with an injection to do what's called antigen presenting cells, like antigen presenters.
It's the same story.
And then you do that immune system to hopefully give it even more targets to hone on.
Exactly. It's the same story. You think that, you do high doses of therapy into a tumor to kill the tumor. That's not the reason you're doing the high doses of chemotherapy.
No, you're doing it to just unenvelop it, get it out the citadel.
Educate the immune system so that it can now go to other tumors, and there's a fancy name for it. It's called the abscopal effect. Mm-hmm. It means that a tumor in your left arm, if it gets an appropriate immune response, all of a sudden those immune cells can go to the tumor in your right arm because they've been educated.
Exactly.
And they know how to kill the cells in your left arm, so they now know how to kill the cells in your right arm or whatever. But that said, there's a logical way to move forward, and we are in the middle of that logical way. And the only way that we can do that, and this is going to be my last plug, is to restore what was broken by COVID, which was the clinical trial system. We have got to restore the clinical trial system because the clinical trial system was desperately broken by COVID. Nurses left, coordinators left, physicians left, emergency room physicians left. So we need to restore it so that all of this knowledge that we're collecting, including the knowledge that we're collecting at Faeth, can now become converted into clinical realities.
That's huge. That's one of my big pushes lately. Because when people say, well, why we haven't found the cure, again, singular, but why isn't this, that, and the other, it's because you need the data to show. And now I explain how phase 1 and phase 2, There's a reason people say, well, trials are guinea pigs, this and that, because back in the day, back, it's like you drip enough poison to see if it kills the human subject or not. That was science-y and Mad Hatter stuff. We are light years away from what that was, right? Like that was the favorite one, cytotoxic, and phase 2 doesn't work. Now it's like a lot of what we're doing is stuff that we already know works with cell biology or with targeted even, things in other tumor types. It's more like that splitting hairs and then splitting the keratin cells and stuff to really be able to say, these are the constituents. And like you said, the sequence, I'm so glad you said that because I keep saying multimodality, but we mean multimodality in sequence. That is going to help just dismantle. It's kind of death by 1,000 paper cuts. It's like if you can't beat the person.
And also the sequence is scientific. It's not
it's scientific. It's not like, right.
Spaghetti on the wall. It's one by one, and there's a reason behind it.
Right, so, because we know the science on normal cells. And I mean, we've studied, you used this term at some point, on the shoulders of those, before us. We're literally taking what we've learned in observation stuff, even if it didn't directly relate to pancreas, taking those concepts, which is what science is, and attacking essentially something that is, again, normal cell, but we're doing it based on completely, observational, understood concepts, and that's huge.
Absolutely.
Now, on that note, I'm going to use this analogy, and you're probably going to want to just throw up or never talk to me again, but tell me if this kind of makes sense for our viewers, because I like little 30, 60-second clips about really like salient points that you're making. And to your point about sugar and sugar metabolism and starving it and not starving it, and how you're saying it's not just a matter of like if you have it, but it's what you do with it. What came to mind? Oh my God, I'm so embarrassed. My hero is I'm going to say this. If you get into a hot dog eating contest, and you didn't know how that hot dog eating contest worked, and somebody said, you're going to eat as much as you can, and this is some big guy that's just a dude, I can put down some hot dogs, he will unequivocally lose, right? He's just going to try eating the hot dogs. And imagine a world where you only had hot dogs for that matter. The reason he loses is not because he can't eat or eat fast. It's because when you see a competition, you notice the way they're using it. They like put in the bread first, put in the water, make it like much easier to swallow so they don't struggle, and then like chop up there's an actual complete, it's the same stuff, the hot dog and the bun and the water, but they use it in a manner that completely, if you took away the water, that person that's the best in the world cannot win. Like, you just cannot win. If you made him do the water at the end, or just at the beginning end, he cannot win. So you've taken the arguably, what's his name, Tagasaku or whatever, you haven't changed the person, which is the cancer cell. You haven't changed the tools, which is the bun, the wiener, or whatever the PC term is, and water. But you've done something about it to where you've dismantled that guy from winning any competition just because of of how it's used. And again, it's a very rudimentary example, but I hope that can help people appreciate it's like, oh, it's not a simple thing of just take all the hot dogs. Like, obviously, then nobody can eat. But there is some ways to use, like with limitations, if you can only use this much water versus an amateur.
I love the hot dog analogy. Use it more and more.
That just came to me, I mean, based on your description, but I think it's pretty accurate.
It's exactly right, which is that it's not that we're removing sugar or nutrients from the environment. It's the way that we are removing the mechanisms or the internal, what I call the internal digestion of a cancer cell that allows the cancer cell to succeed over a normal cell. That's right. The difference.
That's the difference. That champion is still like he's still the fastest whatever under those circumstances, but he's robbed. And you didn't do anything to him. You didn't change his mouth, his tongue, his taste, nothing. You just monopolized the way that he was able to like put himself ahead of the rest. And that's why an amateur will never win. This is amazing. That's a great way, a very surprising way to end with something so amazing with hot dogs. It's America for you. Dr. Mukherjee, this was a true honor, true pleasure. I just can't wait to start funneling and helping people that are really, the one thing about COVID is it made people very curious and feel more ownership and responsibility and wanting to have some empowerment and control over their medical decisions, and especially when it relates to cancer. So I think that is some, the positive where we can capitalize. This is going to help. We're going to funnel people there because people care about diets and care about these things, and I'm just so excited.
And the last message is enroll in clinical trials, because if you don't, or if one doesn't, nothing will advance.
100%. Thank you so much, Sid. This was amazing.